Okay, before I talk about the picture, let me try to explain something I didn't explain in the last lecture, which I think is sort of useful. So, well, I mean, the statement is easy to prove in different ways, but the method of proof is useful and instructive. So what I want to show is that the vertex set of the hypersimplex is given by all these vectors ei, where I is a k-element subset of bracket M. Okay, so remember that the hypersimplex is the subset of the cube 0, 1 to the n. Okay, this should be D. Where the sum of coordinates is equal to k, right? And ai is just the sum of basis vectors. Okay, and so I mentioned you can kind of prove it by, the proof basically goes like this. You choose a vector h, and then you compute the corresponding phase of h, and then somehow you show that ei maximizes the dot product over all vectors satisfying this condition. And you can do this, but it's sort of annoying. If you actually try to do it rigorously, it just takes a while, because I mean, intuitively it should be clear, right, that if you have a vector that has like a bunch of, you choose k maximal coordinates, and then you try to maximize the dot product like that. But let me show you another way to prove that, and which I think is sort of interesting. And so I want to find the set of vertices. And notice that my hypersimplex is given as a sort of as an H polytope. It's given by inequalities rather than as a convex hull of a bunch of points. So how do I, in terms of inequalities, how do I characterize the vertices? Okay, intersection of, right, so I have these inequalities, right, so let me write them down. Maybe I should even write them down like this. X in R to the G, where each xi is between 0 and 1. So I have these inequalities. And you're right that each vertex is an intersection of some of these hyperplanes, right? Some of these inequalities become equalities. But I mean, every face is an intersection like that. So what separates a vertex from any other face? Yeah. Right. Oh, so you're characterizing all these vertices of the hypersimplex, which is what basically we are trying to prove. Right? But how do we? So let's say forget about the hypersimplex, and let's say we just have a bunch of inequalities. Yeah. Zero-dimensional. Okay. So a face, right? Vertices are zero-dimensional faces. And in terms of inequalities, we had like one of these properties that I mentioned in lecture number 2, is that a vertex is a point where you have as many inequalities become equalities as possible. There was some characterization where sub I is a vertex if f sub j is empty for all j strictly contain I. That was one of the characterizations of the vertex. So, and this property is what I want to illustrate right now, is that this property is very useful for determining the vertices of the hypersimplex. Suppose x1 and z is a vertex of a hypersimplex. Then basically I have these inequalities, right? Then some xi's are going to be equal to 0, and some xi's are going to be equal to 1. And what I'd like to prove is that x is of this form, which basically means that each xi is either 0 or either 0 or 1. No xi strictly in between 0 and 1. I want to show that each xi is either 0 or 1. And okay, so how do I prove this? And suppose otherwise xi is strictly between 0 and 1. Then what do I do? Yeah. Oh, you want, but let's say we have no h, right? I just want to look at the hyperplane. Oh, nice. Right, because the total sum is an integer. So if you have one entry between 0 and 1, then we have 0 to xj between 1, or some j not equal to I. And then what do I do? Okay, right, so then I wanna then what I want to do is I want to increase xi and decrease xj, preserving the sum, so until one of them becomes 0 or the other one becomes 1, something like this, right? So I can replace xi, xj by something that, yeah, I actually have a formula here. Do I have a formula? Okay. Formula is 0 xi plus xj if sum is less than or equal to 1, or by I plus xj minus 1 comma 1 if sum is bigger than 1. Each xi is between 0 and 1, so this thing is going to be at most 1. Yeah, you can check that each coordinate is at most 1 and at least 0 in each case. And the sum is preserved, so, and each of these has strictly more inequalities being equalities. Here xi was non-zero and not 1. Here xi is 0. Do you see what I'm? Okay. So get j I fj not empty. That's a contradiction. All right, yeah, so that I just wanted, because later, maybe in your homework or whatever, you're gonna want to use some method like this. Sometimes taking an h and computing the maximum is not as easy as in our examples. Okay, anyways, so by the way, somebody, for those who came in late, I have pictures of the Permutohedron. Yeah, just could you pass them to some people in the back? So the Permutohedron. Oh yeah, you want a picture? It's on both sides. There's two different pictures, which if you look closely at the two pictures on both sides, you're going to see that they are not exactly the same. say it again. So you're saying this property is not known yet?
No, it's not.
Right, it's not an if and only if. That's true. Well, okay, you're right, but yeah, there is. Okay, you're right. What I should have said is that there was this extra, more strong property, is that for every vertex. Yeah, right. So Nikita is saying that another way to show this is that your point belongs to the convex hull of two other points in the polytope. Yeah, but anyways, you're right that this formula doesn't follow because in general you could have redundant inequalities here. But okay, let me try to formulate the correct property then. Correct property is that lemma. Suppose that you have a polytope which is given by g1 of x, gm of x. Then suppose, let's say I have a point x in P at I is a set of all I in bracket M such that gi of x is 0. Then x is a vertex if and only if f sub j is empty for each a not containing I. So this is the lemma I'm using here. Okay, proof exercise. All right, any more questions on this? Okay, Permutohedron. So I defined the Permutohedron last time. I remember Sn is the group of permutations. And the Permutohedron S of n is just the convex hull of all permutations of the vector 1, 2, 3, all the way up to n. W of 1, W of 2, the way W of n, where W is a permutation. And we gave some examples of the Permutohedron last time. So examples of Permutohedra, let's say for n equals to 2, the Permutohedron looks like a line segment. And for n equals to 3, the answer turned out, well, okay, let's actually try to rigorously understand what the answer can be. It's, we mentioned that the dimension is 2, right? Dimension of pi n is n minus 1. So it has to be a polygon. It's a polygon which is defined as the convex hull of 6 vertices. Well, of 6 points, which some of them may or may not be vertices. So a natural guess would be that it should, maybe all of them are vertices, and then it looks like a hexagon. but maybe not all of them are vertices. We are yet to figure out which ones are vertices. And then you can write the coordinates 1, 2, 3, 2, 1, 3. Actually, there is a, can somebody tell me what the next vertex is going to be here? What are the coordinates of the 6 vertices in counterclockwise order? What's this one? 1, 2, 3 is already here. Okay, the top is going to be 3, 2, 1. That's good. And this one is probably going to be 3, 1, 2. Okay. 2, 3, 1. Center is 2, 2, 2. Here, here? Oh, here. Okay. Oh, you want 1, 2, 3, 1 here. And the bottom left is 1, 3, 2. Okay, and then this one, 3, 1, 2, right? And plus 1, just 2. Okay, right, that's true. X1, etc. N should be equal to n plus 1, just 2. Correct. Okay. So let's find the set of vertices of the Permutohedron. Let's see what happens in general. Like, does it actually have 6 vertices, or I mean, n factorial vertices, or does it have less or more than n factorial vertices? What do you think? Yeah. Nice. Okay. Yeah, I think that works. So, all right. Claim phi sub n has the vertex set. Phi sub n is the set of all the. Yeah, let me actually introduce some notation. So I'm going to denote this vector by x sub w. W of 1, W of 2, etc., W of n. So the vertices are just the set of all x sub w's where w in is a permutation. And you're right that I can sort of prove it by induction, choose the maximal coordinate, and etc., etc., etc. And yeah, there's a perfectly fine proof. I mean, any fact about the Permutohedron is sort of can be proven in many ways. But let me show you a proof which is sort of, I'm going to cheat a little bit. And so first of all, clearly the vertices of the Permutohedron are contained in this set. H vertex of the Permutohedron is in this set x sub w. Why is that clear? Right. Yeah, it's by one of our properties from the lecture number 2, which is that if your polytope is given as a convex hull of points, then the vertices are going to be among those set of points. Okay. Now the next point is that phi sub n has at least one vertex. Would be true. And the next step is I'm gonna say that's it. I'm done with the proof. And why am I done with the proof at this? Because it's symmetric. Sn acts on Rn by Permutohedron coordinates, and it preserves the Permutohedron. So each xw is a vertex. Okay. At least one of these has to be a vertex. Therefore, each one of these has to be a vertex. So this is pretty. Yeah, the symmetry idea. All these the hypersimplex and etc. The simplex, they are Sn acts on each of them and preserves each polytope. So you can use that symmetry in your proofs. So okay, that's nice. The vertices are nice. And then the next question is, what are the edges of the Permutohedron? Or more precisely, I know the vertices, so let's say V and W are two permutations when is xv, xw, the line segment, when is this an edge? Yeah. Something related to the Bruja order. That's a good guess. Because this hexagon looks sort of related to the Bruja order. If you know what it is, if you don't know, I'm going to tell you. But okay, so what is the condition? And let me actually try to figure it out. So let's say I take h, a vector h in R to the n, and then I want to. So what is the condition that, so each h, you have your Permutohedron, you have your h, and then there is some set of vertices where h takes the maximum value. So I would like to find a condition that h sub xw, I want it to be, let's say, bigger than h sub xu for all u. Question is, when is this true? Yeah. Okay, that's interesting. So you're saying that V and W should differ by a transposition of two. Yeah, that's very interesting. So yes, I guess there's two questions. Question number one, question number two. Guess for question number one is that if and only if xw minus xv is equal to ei minus ej for some I not equal to j. Okay, does that sound simple? Okay, we interchange 4 and 1. Okay, so you're saying that this guess contradicts the picture that I gave you. Okay. And what about this picture here? Can we have a transposition of 3 and 1 in this picture as an edge? That's all confusing. everybody should be confused at this point because the picture, yeah. Okay, so you're saying when the difference is like twice ei minus a j, that means that it's not an edge. Okay, they have to be. So it sounds like this guess should be correct then. Oh, interesting. Interesting. These are not the same picture. As I mentioned at the beginning, these two pictures are not quite the same. And yeah, I'm going to explain this later. So the purpose is to confuse you slightly right now so that later in life you're not confused. Wait, you're saying these? Not one of them is regular and the other one is not? Button. Okay. All right. Yeah. Anyways, that's very confusing. And so let's actually try to figure it out. Let's say you have you want to find the condition for H to have the dot product maximized at XW. What is the condition on H for this to be true? Well, if it's a non-strict inequality, then it doesn't, right? It can have all coordinates the same, and this would still be true. Okay, the order of the coordinates of x, right? And so what I should write down is that this is equivalent to something like hw of 1, maybe hw of n is bigger than hw of n minus 1, hw of 1. Is that correct or correct? Okay, yeah, that's actually not correct. I should be the inverse. W inverse, W inverse, W inverse. Because, well, you write h xw, what it's going to give you is h1 times w of 1 plus h2 times w of 2 plus etc. So I mean, w of 1 could be any entry. So I guess somewhere in here, if w of I is equal to 1, that means that h w inverse of I should be the minimal, right? If w of 2 is equal to 1, then h2 should be the minimal coordinate. Okay, so this is the condition, and in particular, if you have two permutations v and w, and you want this condition to be satisfied only for v and w, then you would have to say that basically there should be some hv, and yeah, anyways, let me write down an actual statement. The actual claim is that indeed this guess is correct. So xv, xw form an edge of the Permutohedron if and only if, and let me write it down in the following way. So I want to, if and only if, I want to say that w is equal to si times v for some I in bracket n minus 1. So what do I mean by si? Si is the simple, it's called a simple transposition. Simple transposition. So, and I can multiply permutations. So this is a permutation. Si belongs to Fn is a permutation which transposes I and I plus 1. And what do I get when I multiply? I can multiply. The permutation group is not commutative. I can multiply on the left, and on the right, I'm going to get different results. So when I multiply on the left, it means that my two permutations differ by i.e. V and W differ by swapping two adjacent values. Like in this picture here, these two form an edge because I swap 1 and 2, even though they're not, 1 and 2 are not placed directly next to each other. Okay, so you want me to switch. Okay. Yeah, okay. Yes, that's good. That's better. I always always confuse these two. But yeah, anyways, the point is that, and that's the difference between these two pictures, right? So by the way, both of these are from Wikipedia. They're on the same Wikipedia page. And so this picture is where the labels are just coordinates of your. And as I'm going to explain later, sometimes it's convenient. So remark. A lot of times it's convenient to label vertices of Permutohedron by inverses of permutations. But we're not going to do this just now, just yet, but that's where the second picture comes. In the second picture, the vertices, these labels are not the coordinates, they are permutations which are inverses of the coordinate permutation. Okay. Any questions? Questions so far? So when I say adjacent values, I mean that x sub v is a vertex. It has in some position, some coordinate is equal to I, and some coordinate is equal to I plus 1. And then xw is obtained. You swap I and I plus 1, even though they may be in very far away other positions. Oh yeah, for the inverses, you in this case, the condition is that preserving the same notation for xv and xw, xv inverse, xw inverse is an edge if and only if w equals to the other way. Well, if and only if w equals to what? W equals to si v, if and only if v and w differ in adjacent positions. Okay, so in particular in this picture here, you're allowed to swap, like when 1 and 4 are right next to each other, you're allowed to swap them. Okay, now interesting. This should be related to the Breuer order, but that's not quite the Breuer order. That's a good observation, and actually, that's something called the weak Breuer order. Yeah, I'm going to explain that. It is there's two versions of the Breuer order, and that's not the one you know. Okay, and now let's say I want to know everything about the Permutahedron. So the next question is, what about arbitrary faces? Of arbitrary dimension. I should preserve this. What do the faces correspond to on the Permutahedron? Okay, so you're saying that you want some of these, but not all, to just become equalities, maybe. Okay, and that is gonna, well, and then I also have to fix the, let's say, so that corresponds to like a partition of my set. I can partition my set into, so if I have a h double inverse of n, h double inverse of 1, then maybe I declare this is an equality, this is inequality, equality, equality, inequality, something like this. That means I subdivide my set of coordinates into parts. And within each part, I declare that this part should be bigger than this part, and etc. And that's kind of nice. But then for each part, I also have to specify which coordinates go into that part. So if I swap W inverse of n and W inverse of n minus 1, then I should remember the set that these two indices. Yeah, anyways, let me try to state the, but it's a correct guess. But let me, so here's the actual result, that the faces of the Permutahedron are in bijection with certain combinatorial objects, which are called with ordered set partitions. And what is an ordered set partition? Just by definition, so I'm gonna try to bold phase. This is going to be the bold phase B. This B is a tuple B1, B2, all the way up to BK, where each BI is non-empty, and bracket n is the disjoint union of these. B1, B2, all the way up to Bn. So I claim that each phase uniquely gives me an ordered set partition, right? So it matters which part is the first one, which is the second one, etc. These are these parts here. Yeah. B1, B2, and yes, I should write this bijection down exactly. And first of all, what is the dimension? The dimension of each phase for, if you give me a bold phase B, what's going to be the dimension of the corresponding phase if it's of this form? n minus k. Right, thank you. Is n minus k. Right, so I split my coordinates into k different parts, and then I declare that in each part the coordinates are the same, so they have sort of n minus k degrees of freedom. All right, yeah, that's a non-rigorous explanation. But so let me actually, I should write down some sort of a proof for this. And in the proof, I want to explicitly write down each phase. So let's say I fix a B partition like this. And I want to find a phase which corresponds to it. And as we know, phases are given. So I want to find a phase of the form f sub h, where h is a vector. I want to find some vector h, which depends on my partition, such that the corresponding phase somehow in bijection with this partition. So I can actually do that pretty easily. Choose h of b r to the n as, so I can choose my vector satisfying the following two conditions. First, I want the coordinates inside each part to be the same. hs is equal to ht if s and t belong to the same part. And then I want the coordinates to be ordered. I want the coordinates in B1 be bigger than in, or let's say less than the one is in, yeah, let's do bigger. So xhs is strictly, well, non-strictly, but bigger than ht if s belongs to bi, t belongs to bj, and I is less than or equal to j. Okay. So I choose my h vector like this, and then basically I can figure out which permutations correspond to, the permutations that correspond to h are going to be, basically you fix the first, the maximal B1 elements, and then etc. Okay, anyways, you can, okay, I actually have it written down. Let me write it down. The answer is going to be. For some proofs, I want to be sort of at least slightly rigorous. F(h) of B is the convex hull, all permutations x of w, where w is, in a sense, satisfies w of s bigger than w of t for s in bi, t in bj, and s. Okay. So instead of here, I have non-strict inequalities, and then I basically take the set of permutations which resolve those inequalities. Kind of, I break the ties between the coordinates of h using these permutations. And then, so these are the vertices of my phase. And that's basically it. I just wanted to give you an explicit description, because it's one thing to say that phases are in bijection with partitions. It's a whole other thing to actually, you have to describe these bijections explicitly. And so in particular, now we can compute the, let's say, the f vector. The f vector of the Permutohedron is given by, first of all, what is f -1 and f n minus 1 of the n? One. Okay. What is f0 the n? And factorial. All right. And well, okay. How about this? What about fn minus 2 of by n? Because we know fn minus 1 is equal to 1. So that's the number of facets. How many facets does a permutahedron have? Let's actually count. So for the hexagon, I get how many facets? 6. And for the three-dimensional permutahedron, how many facets does this one? 12. All right, interesting. 12. Wait, is it 12? 14. That's better. 14. And okay, so what's the general number? Hmm? Kähler numbers. Yeah, that's actually not true. No, it's a much simpler number. Which actually, I mean, you can figure it out from the proposition here. Just if you look at this proposition carefully enough, say again. 2, I can't hear you. 2 to the n minus 2. Interesting. To the n minus 2. And why is that? Okay, nice. Right, okay, so indeed, the dimension of each face is n minus k. If you want the dimension to be n minus 2, you want k to be 2, which means that for facets, b is just b1, comma b2, and b1 could be, well, the disjoint union from b1 and b2 is n, bracket n, and each bi is non-empty. So you basically get 2 to the n minus 2 options for the face. And yeah, in general, these are related to the Stirling numbers of the second kind, what those are. But yeah, anyways, that's it for today. Thanks a lot for coming and have a good weekend. I'll see you all on Monday.